Okay, time for more properties of sound. You made it through the first one, so now let's talk about overtones, tuning and temperament, and the spectrum. Let's start with overtones. So, timbre, I said before, was kind of a TLDR situation. It really is. Well, this is the part where we dive into that. In order to really explore it, we need to look at how audio is represented. And waveforms are great, but they don't give us the full picture for a couple of reasons. Primarily, classical waveforms like sine, triangle, saw, and square are not going to exist in most real-world scenarios. Particularly for instruments and voices, they're going to change over time. You're going to have changes to the waveform. It will not be a nice, pure, periodic, repeating signal. Number two, the resonance of an object and how it filters the sound being produced can create other overtones. Overtones are notes above the fundamental that resonate in sync with the fundamental, but at lower amplitudes. These are also called partials or harmonics. We're going to avoid the term harmonics for a reason that we'll get to soon enough, but they are any sound other than a pure sine wave is going to have these overtones. A pure sine wave has no overtones, but every other sound has some sort of other component other than the initial fundamental frequency with overtones occurring at significantly lower amplitude. Brass players are going to know these really well because they're the notes that are available at each valve or slide position. So the fundamental is the lowest note in the overtone series. And in music notation, this is the pitch that's actually written down. This is, if you see C, C is the fundamental. If you see B flat is the fundamental. The overtones exist over that, hence the name, but the actual note you hear is the fundamental plus the first overtone, partial, the second partial, so on and so forth. Again, the terms partials or harmonics can be used interchangeably, but I'm going to recommend partials because harmonics can be confused with enharmonic. You know, why is D sharp the same as E flat? Well, in equal temperament, they are. And inharmonic, and we'll talk about harmonic and inharmonic in a little bit. But enharmonic means that they are the same pitch and equal temperament. Harmonic means that it is in a mathematical relationship to the overtone series. So it's one of the partials. It's a nice whole number multiple. Whereas inharmonic means it's not following the overtone series. So it's partial 3.14 or 2.758721Q, but not partial number 3. So math time. Calculating frequency of a partial is actually really, really easy. You take the fundamental and you multiply it by a whole number. So fundamental times 2, fundamental times 3, fundamental times 4 or 5 or 6 or whatever, but whole number multiples. That is the key. Here's an example. We start off with 110 hertz, which is A. Then you double that to 220 hertz. Then you triple that to 330 hertz, quadruple it to 440 hertz, quintuple it to 550 hertz, and sextuple it to 660 hertz. All of these are valid partials for that first fundamental of 110 hertz. And all of those could be played together, although after 110 hertz, you're going to have a really, really, really significant drop off in amplitude. And that would give you a very interesting timbre of that A, 110 hertz, with just a very, very interesting way of hearing it based on which partials are occurring at which amplitude. Here's another example. We're starting on the tone C, and then we have the octave C, then we have the perfect fifth tone, then we have the next octave, then the major third, and then the perfect fifth. These are typically how things are going to happen in terms of the frequency. So we've got frequency times 2, times 3 for the G, times 4 for the next octave, times 5 for the major third, and then times 6 for the perfect fifth. And that gives us the overtones in sequence. So again, it's always the partial number multiplied by the fundamental frequency, but this assumes a perfect whole number or pure ratio tuning that does not really work in the real world. Why? Well, because of tuning and temperament. So classically, historically, all instruments are tuned by taking the fundamental and deriving the other notes in the chromatic scale in relation to that fundamental. So you would start with the fundamental, then go to the octave, which is a 2-to-1 ratio. Then the perfect fifth, which is a 3-to-2 ratio of partial 3-to-2, followed by the perfect fourth, which is a 4-to-3 ratio, partial 4-to-3. Then a major third, which is partials 5-to-4, a minor third, which is partial 6-to-5, etc., etc. Once you get those kind of spaced out, you would use octave doubling to fill stuff in. It's more common to tune by perfect fifths and then use octave doubling to fill it in. So here are the musical interval ratios. Unison, minor second of that awful 16-to-15 ratio. Major second, minor third, major third, perfect fourth, diminished fifth, perfect fifth, minor sixth, major sixth, minor seven, major seventh, and octave. Obviously, some of these are going to be easier to hear and thus to tune to, like the octave and the perfect fifth and the perfect fourth. Others not so much. That minor second, kind of hard. The problem, though, is that tuning by fifths and then using octaves to fill in will result in a gradual drift in pitch as you get higher and higher up. This is called the Pythagorean comma, and it's a rounding error of 23.46 cents. And a cent is a logarithmic unit for measuring really, really small musical intervals. Each semitone, so from A to B flat, is 100 cents. G sharp to A, 100 cents. G to G sharp, 100 cents. So that is always going to result in a scale of 1,200 cents from the fundamental to its octave. What this means is that 23.46 cents is slightly less than a quarter tone, which would be 25 cents. Most people, your average Joe six-pack out on the street, can hear that 25-cent difference. Most musicians can hear down to 9 or 10 cents, and then people who train and study can hear a difference of as few as 5 to 6 cents, but no one ever can hear a difference below 4 cents or less. That is not possible for the human ear to perceive. So you have a little slight error around 4 cents. Those start getting bigger and bigger and bigger, but also you will notice that the math does not work. So how do you get rid of the Pythagorean comma? Well, you can hide it. You can bias certain intervals to sound better or worse than others. This is temperament. And historically, it was used to tune large keyboards like pianos, harpsichords, and organs. But there is a big problem with this. Playing in a specific temperament makes it so that some intervals sound great and others sound horrible. A great example is mean tone temperament. Mean tone temperament, if you're playing in the key that it's set to, the thirds sound amazing. They sound absolutely divine, like angels singing. But your fifths are slightly narrowed. And that means that each fifth is abrasive and slightly out of tune. And as you get away from the initial key, they start becoming more and more so. Usually with the keys, you can typically play in the fundamental, the fifth, and the fourth. Others are going to sound really, really bad. And especially as you drift out towards something like the tritone, those are going to sound particularly awful. This is why Bach's well-tempered clavier was so revolutionary, because now instead of being able to play in 2 or 3 keys, on any given instrument, you could play in all 12 major, all 12 minor, and it was perfect. Because if everything's out of tune, nothing is out of tune. And that is the solution, equal temperament. The ratio between each semitone is identical. So everything is slightly out of tune except for octaves. Octaves are preserved so that they are always perfectly in tune. And again, you can now play in all 12 keys. But other considerations, there are literally thousands of ways to tune or temper a musical scale, and most cultures do not use the Western 12-tone equal temperament or 12-tet scale. If you want to play with that, get a copy of the Scala program and download its basic examples. There's like 5,000 plus scale files in there, all of which are different scales, different temperaments. You can also check out the Zenharmonic wiki if you want to get into that more, or set up time to meet with me. I will be more than happy to show you how that sounds using a violin or some other fretless instrument. And here are the musical ratios, and here is how that works in terms of things like the cents and the bridge length on a stringed instrument with frets. But let's move on. So now that we know that there's a lot more than one single frequency being played because of the overtones, let's look at how we view that data. Most DAWs, not all of them, Pro Tools, and other audio programs have two ways to do that. You have the spectrum view and the spectrogram view, which is also called a sonogram. Spectrum view shows frequency as the x-axis and amplitude as the y-axis for a sound. The amplitude is different from waveform view because the spectrum shows the amplitude of each partial, while the waveform shows the amplitude of the overall signal. Typically, this can change with time as the signal changes, so you're going to have a display that's morphing and you'll see peaks spiking up and down at different points. It's very cool. Spectrogram or sonogram view shows time on the x-axis and frequency on the y-axis, with the amplitude shown by the intensity of color, which varies from program to program. Typically, you will have either black and white or red or a rainbow color scheme. It really does depend, but you will see that lower, closer to the fundamental, the color is much more intense. If you're doing red, this is going to be absolutely scarlet blood red, and then it's going to fade to pink at the higher amplitudes. Let's take a look at those. So here we have a signal. It's just a saw wave on top. And then below that, we have the spectrum view, which is showing the fundamental is occurring at 100 hertz, and then we have different signals occurring at 2, 3, 4, 5, 6, 7, 8, and 900 hertz, and at significantly lower amplitude intensity. So this is giving us a view of the fundamental and the first 9 overtones, effectively. Another way of looking at it, this is a spectrum that's showing a little bit closer to what you would see in a DAW. You have the frequency, and it's showing spikes where you have really, really big, nice bumps in the overtone partials. So you've got a fundamental at 50, overtone at 150, 250, 350, 450. There's other stuff present there as well, but you can see it's nowhere near as important. That could be noise bleed on the signal. It could be something else. It could be filtering. Who knows? Here we have the sonogram view. This is the cool one. So if you look at the waves that are going across the screen, starting at 0, a little bit after 0.5 to about 1.35, and then at 1.5 all the way to 2.9, you'll notice that it looks like you have a cascading waterfall of different signals. Those signals are the overtones. If you take a look at where they are, the first one is occurring roughly at 200, then at 400, then at 800, and then they're going up. The scale is over on the right side. But you'll also notice that they're not as intense at certain points. That some are more intense, some are less intense, and as they go up higher and higher in frequency, the intensity definitely trails off. So this is a really, really great view to look at if you want to see what frequency components are being used in any given sound, and in some programs you can actually edit those as well. So let's get into the spectra and the Fourier theorem. This is time for some math, but I will promise to make this as painless as possible. So we've already said that the sine wave is the basic, irreducible atomic unit of sound. It has no overtones of its own. Nothing can be reduced further. You have no subsine wave of any type. Cool. What does that mean? Well, I've already alluded to this in the last video, but it means that we can generate any other waveform by summing together different sine waves of diminishing amplitudes in order to recreate a periodic signal. So what we're doing is we're taking the sine as a fundamental, and then we're adding sine partials from the overtone series, but we're doing it while reducing the amplitude of the partials. Otherwise, we just have a chord of sine waves, which is boring. Who cares about that? This is the Fourier theorem, that any periodic signal can be reproduced as the sum of sines at varying amplitudes. And its application in this way is called Fourier synthesis, or more commonly, additive synthesis. Now, you can also reverse this to deconstruct a complex periodic sound into its sinusoidal components and amplitudes, which is a process called Fourier analysis, which we will look at a lot more in Music Tech 2 and interactive computer music. But that is how the sonogram is displayed. It is performing Fourier analysis in order to get those sinusoidal components and display them. So, summing sines to get other waveforms. All of the classical waveforms can be derived from sines. For example, a triangle wave contains only the odd numbered partials, but their amplitudes are inversely proportional to the square of the partial. So if you have partials 1, 3, 5, 7, and 9 present, then the amplitude of partial 1 is 1. The amplitude of partial 3, well, 3 squared is 9, and then to inversely proportion that, you just divide that by, you divide 1 by that, so 1/9. Okay, partial 5, well, we square that, that's 25, so that becomes 1/25. 7 squared is 49, so 1/49, and 9 squared is 81, so 1/81. Square wave also contains only the odd-numbered partials. Note that I said square wave, not pulse width modulation, or PWM wave. But with the square wave, their amplitudes are inversely proportional to the partial number. So partials 1, 3, 5, 7, and 9, you have amplitudes 1, 1/3, 1/5, 1/7, 1/9. And a sawtooth wave contains even and odd partials, and the amplitudes are inversely proportional to the partial number. So for partials 1, 2, 3, and 4, and 5, you get 1, 1/2, 1/3, 1/4, and 1/5 for the amplitudes. It's pretty cool. Now, we talked a little bit about harmonic and inharmonic spectra. Let's just revisit that. So the examples above are all using partials that follow the overtone series. It's nice whole-numbered multiples of the fundamental, no decimal points. That means it is harmonic. You are multiplying by whole numbers to get the partials. But that is the textbook example, but it's not the real-world example. That is a very small subset of all possible sounds, but it tends to be the sounds that we think of as being musical or otherwise aesthetically pleasing to listen to. Most sounds do not follow that nice whole-numbered multiple sequence. What happens instead if you don't have whole numbered partials or the ratio to the fundamental? You get inharmonic partials. So if instead of having partial 7, you have partial 7.1764, but all the other partials are nice and harmonic whole number multiples, it shapes the timbre and creates a more distinctive sound. The result is that the filtering that you hear from the body of an instrument can slightly deviate and cause changes in which partials are emphasized. So you might get one of those weird deviated partials like that, but others will be primarily harmonic. This creates the variety that you hear in different instruments. But what if it's really out of whack? I can hear you thinking that. What if instead of having nice partials like that, I have partials 1, 2.7829, 13.125367, and 87.134507? If all of the partials after the fundamental are inharmonic, you're going to get something really metallic and bell-like. I'm not really sure why. I don't think anyone really is. But these inharmonic partials, they sound very metallic. And this is something that you'll experience a lot when we get into frequency modulation synthesis in particular. It's a very, very interesting phenomenon, and we'll play around with that quite a bit. Also, keep in mind that noise has a spectrum as well. If you look at a spectrogram or a sonogram, you'll notice that white noise has a spectrum of equal energy distributed across every frequency. You're just going to see like a solid speckled band of static. Pink noise has a spectrum of equal energy distributed across each octave, so it will be much, much more intense at the lower level and then staticky, but it will still get lighter and lighter as you go up. The result of that is that we hear white noise as being louder because as the frequency increases, the interval size increases, because again, it's exponential. So the energy distribution also gets larger and louder as we get higher and higher in pitch. What that means for pink noise is that the octaves down at the lower level are going to be more prominent. So it sounds quieter and more bass heavy because we're distributing energy across octave bands, not by every single possible frequency. So how do you change the timbre? Well, the easiest way is to use an equalizer. This lets you boost or cut different bands of frequencies independently of each other. And there are two primary types that we're going to look at. The graphic EQ, which typically has bands defined by the manufacturer and cannot be changed. You can't say, oh, I don't like that we go from 130 hertz to 160 hertz. I want to go to 150 hertz. You're stuck with that. There's no way to change the bandwidth or the cutoff of any of those bands. You can just boost or cut the predefined bands. This is the consumer grade stuff that you find on stereos or in programs like iTunes or Apple Music or Winamp for the one person who probably still uses that. Instead, in this class, what we're primarily going to use is parametric EQs, where the user defines the frequency at which the filter takes effect, the cutoff, the bandwidth, how wide the slope is or how much area is being affected, and on really good ones, the Q or resonance factor. This is very, very, very similar to classical filtering, which we'll look at later. It's also very, very common in DAWs and on mixers. I can guarantee if you have Ableton, Logic, or Reaper, you have a parametric EQ. And if you're doing stuff with an actual mixing console, you have a parametric EQ. But play around with those knobs and see what happens when you're playing just a steady noise signal. You'll be really surprised at how you can change the timbre and how, in fact, you can actually focus onto very, very, very super narrow bands and get actual pitched noise bursts if you're really, really inclined to go that route.